So atomic mass, sometimes you'll hear it called atomic weight. Weight and mass are not actually the same thing, but as long as you stay on the planet, they're basically the same. Anybody planning to leave the planet this semester? No, I wouldn't recommend it. So we won't worry about it. The atomic mass is directly below the element symbol in the periodic table. These are not nice whole numbers. These represent the average mass of isotopes that compose that element. They're weighted according to their natural abundance. So if you look at the mass, say, of oxygen of 15.9994, there's actually no oxygen atom that weighs that. There's some that weigh a little more, some that weigh a little less, but that's the average. And since we generally deal, anything we do is with ginormous numbers of atoms, the average is what's useful. It's not useful to have the mass of an individual atom for most things. How do they figure out the mass? Well, here's an example for chlorine. Two naturally occurring isotopes, 35 and 37. They can figure out the mass of these. So chlorine 35 has a mass of 34.97 atomic mass units, and 37 is 36.97 atomic mass units. This number is very close to 37. This is very close to 35. So 75.77% of all chlorine is the chlorine 35. 24.23% is the chlorine 37. So we do a weighted average to calculate the average mass. So we take the percent abundance as a fraction. So 24.23%, the fraction is 0.2423. You take the percentage and you divide it by 100 to get this. You multiply it by the mass of that isotope and you get a mass. You take the other percentage, convert it into decimal form, multiply it by the mass of that isotope, and you get another mass. And you add those two together, this gives you the average mass of chlorine. Any questions? So this is one way of looking at how to calculate that. The fraction of the isotope times the mass of the isotope. And for however many isotopes you have, you just add them all together. Let's do this one real quick. Silver has 46 known isotopes, but only 2 occur naturally. So we're supposed to calculate the atomic mass of silver. And could you just look at the periodic table and see the mass of silver? Yeah, you could, but then we're missing the point of doing the exercise, which is to understand how that number came about. So we're going to take the, here let's do 107 first. We're going to take the mass times the abundance as a fraction. So 5184 times the mass, 106.90509. 0.5184 times 106.90509. I get a whole mess of digits. Now, it's certainly okay to just write them all down. But if you can see into the future and guess how many you're going to need, you could also just carry 2 or 3 extras and not worry about it. What would the unit on that be? AMUs, atomic mass units. Those are used when we're measuring one particle. So the other one then is going to be 0.4816 times 108.90476. And for that, I'm getting 52.4485324. It's just everything in my calculator coughed up. And then we add those two together. I should have been thinking ahead, but I was not. At 107.868131 atomic mass units. Sig figs. We have multiplication and adding, right? So the first thing we did was multiplying. So this should be 4 sig figs, right, out to here. And this one's 4 sig figs with a lot more, so out to here. Now we're adding, so we're looking at decimal places. 2 decimal places, 2 decimal places. Our answer should have 2 decimal places. So, didn't mean to do that. I was trying to do a 2-finger zoom and I missed 1 finger. So 107.87 AMUs. Then we look at the periodic table and it says 107.868. And yeah, that'll be good. If you came up with 500 compared to 107 on the periodic table, something went wrong, right? You can check and see if your answer is reasonable. What we like to do on exams is we like to make up elements that aren't on the periodic table so you can't cheat and just look at the answer. Any questions? What's really fun is when they give you a problem where they'll give you the average mass and then they'll ask you for one of these pieces of information. Those are fun 1A problems. How do they figure out the masses of atoms and the percent abundances? Well, they do it using mass spectrometry. Mass spectrometry separates particles according to their mass. And so this is something that you might, an output you might get from a mass spectrometer, showing that chlorine-35 with a mass of 35 has an intensity of 100%, and this chlorine-37 has a lower intensity. And so based on the relative intensities, you can figure out the percentages. This is what a mass spectrometer looks like. So we've got a couple of really, really big magnets in here. We've got some charged electrical plates. We have a beam that's going to ionize the samples because you can't really accelerate particles unless they're charged. And so we put our sample in here, and there's a heater that vaporizes it and turns it into a gas. And it comes over here, and this electron beam ionizes it, turns it into ions. And then these charged particles causes charged particles. The charged plates accelerate the particles and cause them to move fast. And so they come speeding through here, and then when the charged particles hit this magnetic field, they interact with the magnetic field, and they will be separated based on their mass. So the heaviest particles will have the lowest angle, and the lightest particles will have the greatest angle. They will be the most deflected by the magnets. And so we can separate them by their mass, and this is how we determine the mass of different isotopes, determine the mass of lots of things.